Representation Theory of Finite Groups, Lecture 1, Recap of Group Theory. So let us start with a definition of the group. A group is a tuple which consists of a set G, a binary operation on G, denoted by dot, and a fixed element E in G. So this datum is supposed to satisfy the following axioms. First of all, the binary operation on G is supposed to be associative. This means that multiplying A with the product of B and C, we will get the same result as if we multiply the product of A and B with C. The next axiom is that our fixed element E should be an identity element in the group. This means that multiplying E with any other element A, both on the left and on the right, results in the element A. And the final axiom requires existence of the so-called inverse elements. This means that for each element A, there should exist an element B such that the product of A and B in any order gives the element A, the identity element. A couple of remarks. First of all, one usually denotes a group by its underlying set, G. So the group is a tuple which consists of G, the operation dot, and the identity E, but one usually shortens this notation just to G. Then A dot B is usually written as AB. Then we know that the identity element in any group is unique, and also each element in a group has a unique inverse, which is usually denoted A inverse, or it is sometimes denoted minus A if the binary operation which gives a group structure is some kind of addition. Here are some examples. The usual examples of groups are as follows. So we have the additive groups of numbers, the group of integers with respect to addition and with the identity element 0. The group of real numbers with respect to addition and with the identity element 0. Or the group of complex numbers with respect to addition and with the identity element 0. Then we have number groups with respect to multiplication. So for example, the group of non-zero rational numbers with respect to multiplication and with the identity element 1. The group of non-negative real numbers with respect to multiplication and with the identity element 1. Or the group of non-zero complex numbers with respect to multiplication and with the identity element 1. Then we have matrix groups. So we have the group of invertible n times n matrices with rational coefficients with respect to multiplication and with the identity element being the identity matrix. And we have similar groups for real numbers, for complex numbers, and for other fields. Then, given a set X, we have the group of all bijections from X to itself with respect to composition of maps and with the identity map from X to itself being the identity element of this group. The special case of this group is the case where X is the finite set consisting of 1, 2, 3, and so on up to n. Then the corresponding group is denoted by Sn and is usually called the symmetric group on n elements. Then we have groups of symmetries of geometric objects. So if we have some geometric object in some space like Rn, we can consider all isometries of Rn which preserve this geometric object with respect to composition and with the identity map being the identity element of this group. A special case of this construction, which will be used quite often in this course, are dihedral groups D2 times n, so which is the group of linear symmetries of the regular n-gon inscribed in the unit circle in R2, such that one of the vertices is the point 1, 0 of R2. So here is an example. If n is equal to 3, we have 6 symmetries of the regular triangle inscribed in the unit circle in R2. So these symmetries, we can rotate the triangle in 3 possible ways. And then we have the reflection symmetries through the axes which go through each vertex of the triangle and through the middle of the opposite side. Let us now talk about subgroups. Let G be a group. A subgroup of G is a subset H of G, which inherits from G the structure of a group by restriction. So this means the following. First of all, the identity element must belong to H. Then, given two elements A and B in H, their product AB must belong to H. And finally, for any element A in H, the inverse A inverse of A also must belong to H. The usual notation for a subgroup is as follows. So H is a subgroup of G. And a couple of remarks. If G is a finite group, then the last condition is redundant. It follows automatically from the first two conditions. And also, the first condition can be actually changed to the requirement that H should be a non-empty subset of G. Here are some examples. The additive group of all integers is a subgroup in the additive group of all real numbers, and this one, in turn, is a subgroup in the additive group of all complex numbers. Similarly, the multiplicative group of all non-zero rational numbers is a subgroup in the multiplicative group of all non-zero real numbers, and this one, in turn, is a subgroup in the multiplicative group of all non-zero complex numbers. The symmetric group Sn has a classical subgroup An given by all even permutations. The group SLnk of all n times n complex matrices with determinant 1 is a subgroup of the group GLnk of all non-degenerate n times n matrices. So here K is just any field. Also, if K divides n, then the dihedral group D2 times K is a subgroup of the dihedral group D2 times n, since the regular K-gon is inscribed into the regular n-gon under this assumption. So for example, on this picture we see how the regular triangle is inscribed into the regular hexagon. And so any symmetry which leaves this triangle invariant will also leave the hexagon invariant. Okay, let us now talk about homomorphisms. Let G1 and G2 be two groups. A group homomorphism from G1 to G2 is a map phi between the underlying sets of these group structures, which has the property that it intertwines the group operation in the group G1 with the group operation in the group G2. So this means that if we apply this map phi to the product of A and B in the group G1, the outcome should be equal to the product, now in the group G2, of the images of A and B under phi. A couple of remarks. Any homomorphism of groups sends the identity element of the first group to the identity element of the second group. Next, composition of homomorphisms is easily seen to be a homomorphism. The identity map on each group is obviously a homomorphism. And if you put all this together, then we see that groups and homomorphisms of groups form a category which is denoted by groups with bold font. So here are some properties of this category. A homomorphism of groups is injective if and only if it is a monomorphism in that category. A homomorphism of groups is surjective if and only if it's an epimorphism in that category, and a homomorphism of groups is bijective if and only if it is an isomorphism in that category. It's a nice exercise to check all these things, and the surjectivity part is not really trivial. So here are some examples of homomorphisms. So as we already mentioned, the identity map on any group is a homomorphism from this group to itself. Second example, given any pair of groups G1 and G2, the map which sends all elements from G1 to the identity element in G2 is a homomorphism. Third example, if H is a subgroup of G, then the inclusion of H to G is a homomorphism. Next example, the determinant map is a homomorphism from the group of all invertible n times n matrices over a field K to the multiplicative group of all non-zero elements in K. Next example, the map from the symmetric group Sn to the multiplicative group of non-zero complex numbers, which assigns to each permutation the sign of this permutation, is a homomorphism. And the last example, let us enumerate the vertices of a regular n-gon in some way by elements from 1 to n. Then each element of Dn induces a permutation of vertices and hence defines an element of Sn. The corresponding map from D to n to Sn is a homomorphism, clearly from the construction. And note that this homomorphism depends on how we enumerate the vertices. If we choose a different enumeration, we will get a different homomorphism. Next, let us discuss the kernel and the image. Let G1 and G2 be two groups, and phi be a homomorphism from G1 to G2. The kernel of phi is defined as a set of all elements in G1 which ascend by phi to the identity element in G2. And the usual notation is the ker of phi. An easy property is that ker of phi is always a subgroup of G1. Definition: the image of phi is defined as a set of all elements of G2 of the form phi of A, where A is an element of G1. The notation is im of phi, and an easy property is that im of phi is a subgroup of G2. Here are some examples of kernels and images. A homomorphism phi from G1 to G2 is a monomorphism if and only if kernel of phi is the identity element of G1. And a homomorphism phi from G1 to G2 is an epimorphism if and only if the image of phi is the whole group G2. The kernel of the determinant homomorphism from GLN K to K star is exactly by definition the subgroup SL and K, the set of all matrices with determinant 1. And the image of this homomorphism is of course the whole of K star. So any element of K star is the determinant for some non-degenerate matrix. The kernel of the signed homomorphism from Sn to C star coincides with An. So the even matrices are sent to 1. And the image of the signed homomorphism coincides with the subgroup of C star consisting of plus and minus 1. Next, let us discuss cosets. So let G be a group and H a subgroup of G. A set of the form H times G, so which consists of all elements H times G where H is in H, is called the left coset of G modulo H. Symmetrically, a set of the form G times H, which consists of all elements of the form GH where H is in H, is called the right coset of G modulo H. The main property of the cosets is the following. So if we have two elements G and G prime in G, then the corresponding cosets AG and AG prime either coincide or do not intersect. And similarly for the right cosets. So the usual notation for the set of all left cosets is G modulo H on the left, and the usual notation for the set of all right cosets is G modulo H on the right. Another property of cosets is that for any pair G and G prime of elements in G, the corresponding cosets GH and G prime H have the same cardinality. In particular, if G is finite, then the number of cosets G modulo H, both left and right cosets, is equal to the cardinality of G divided by the cardinality of H. So here are some examples. Let us consider the additive group of all integers, and let the subgroup be the set of all even integers. This is clearly a subgroup. Then we have two left cosets of z modulo 2z, namely the coset 2z, the subgroup itself, which consists of all even numbers, and the coset 1 plus 2z, which consists of all odd numbers. Another example, consider the group Sn and the subgroup An of all even permutations. And similarly to the previous example, we have two left or right cosets of Sn modulo An, namely the coset An consisting of all even permutations, and the cosets An times the transposition of 1 and 2, and this is a coset which consists of all odd permutations. Notably, this coset can be also written as the transposition 1, 2 times An. Example 3, for any group G, if we consider the subgroup of G consisting just of the identity element, then both left and right cosets for this subgroup are exactly the singletons of G. Example 4, for any G, if we consider the subgroup H, which coincides with G, then we have the unique coset G. Now let us talk about normal subgroups. Let G be a group. A subgroup H of G is called normal, provided that for any element G in G and for any element H in H, the element GH G inverse belongs to H. So the usual notation is as follows. So H is a normal subgroup of G. And an alternative description of a normal subgroup, H is a normal subgroup of G if and only if GH is equal to HG for any G in G. So each left coset should be equal to the corresponding right coset for any element G in G. Recall that a group G is called abelian or commutative, provided that the binary operation on this group commutes. So A times B is equal to B times A for all A and B in G. And from the alternative description, we immediately have that any subgroup of an abelian group is normal. So here are some other examples of normal subgroups. So if we consider G to be equal to Sn and H to be equal to An, then we have only two cosets, left or right. The one is the subgroup itself, the set of all even permutations, and the other one is the set of all odd permutations. And so we see that each left coset coincides with each right coset, and so An is a normal subgroup of Sn. So here is one form of the notation which we will use for elements in Sn. So when we write them as functions, we write the elements 1 to n in the first row, and then the images of these elements under our permutation from Sn in the second row. So let S denote the transposition of 1 and 2, and T denote the transposition of 2 and 3 in S3. Then we can write S3 as a group consisting of E, the identity, then S, this element, T, this element, ST, TS, and STS, which is equal to TST. So now consider S3 as a group G, and let H be the subgroup given by E and S. Then the coset TH, so we should multiply E and S with T, we get T and TS. While if you compute the coset HT, so we multiply E and S with T on the right, we get T and ST. And so we see that these two cosets are different. So this means that H is not a normal subgroup of S3. Now let us discuss quotients. Let G be a group and H a normal subgroup of G. Then the set of all cosets, left or right, because they are equal, has the natural structure of a group given by the binary operation defined as follows. So if we take the coset GH and want to multiply it with the coset FH, we define the outcome to be the cosets GF times H. And the identity element in this group structure is the coset H itself, which is E times H. We know that the inverse to the coset GH with respect to the structure is the coset G inverse H. So this group G mod H is called the quotient of G modulo H. Remark, if H is not a normal subgroup of G, then the product of two cosets GH times FH taken element-wise is not one coset, but is usually a union of more than one cosets in general. So the same definition gives rise to an associative multi-valued operation on the set of, let's say, right cosets. Now it's a different set from the set of left cosets. So in this way, we get something which should be called a multi-group, maybe. So here are some examples. Consider the additive group of all integers, and for a fixed positive integer n, let H be the subgroup given by all integers divisible by n. Then this is a normal subgroup because Z is an abelian group. And the quotient Z modulo the subgroup nz is usually denoted by Z sub n and is called the group of all congruences modulo n. And this group Zn is a finite cyclic group, so it is generated by one element, the element 1. Example 2, consider G to be the symmetric group Sn and let H be the group of all even permutations in Sn. Then we have already seen that An is a normal subgroup of Sn because it has index 2. Any subgroup of index 2 is normal. So the quotient Sn modulo An is isomorphic to Z2, to the group of congruences modulo 2, by sending An to 0 and the coset of all odd permutations to 1. Quite similar example is the following one. If we consider the dihedral group D2 times n and its subgroup Hn of all rotations, then Hn consists of n elements, so it has index 2 in D2 times n, so it's a normal subgroup, and the quotient is again isomorphic to Z2 by sending Hn to 0 and all non-rotational symmetries of the regular n-gon to 1. Next, let us recall the first isomorphism theorem. So this is Noether's first isomorphism theorem. Let G1 and G2 be two groups, and phi from G1 to G2 be a group homomorphism. Claim 1, the kernel of this homomorphism is a normal subgroup of G1. Claim 2, the image of this homomorphism is a subgroup of G2. And claim 3, the quotient of G1 by the normal subgroup ker phi is isomorphic to the image of phi. And the isomorphism in claim 3 is given by sending the coset G times the kernel of phi to the element phi of G in G2 for any G in G1. Let us now talk about conjugated elements and the order of elements. Two elements G and F in G are called conjugated, provided that there is an element H in G such that the product GH is equal to the product HF. Alternatively, we can write that G is equal to the product H, F, and then H inverse. Conjugation is an equivalence relation on G. And equivalence classes for this equivalence relation are usually called the conjugacy classes in G. For example, if G is abelian, then the conjugacy relation is just the equality relation. So each equivalence class is a singleton. Now about the order. So we define the order of an element G in G at the cardinality of the minimal with respect to inclusion subgroup of G, which contains this element little g. Remark, the minimal with respect to inclusion subgroup of G is exactly the set of all elements in G, which can be written as powers of our element little g. And the exponents of these powers should be all integers. So you should also take into account the negative powers of G, or the positive powers of G inverse. Observation, if G is finite, then the order of G divides the cardinality of G because the order of G is a subgroup. And the cardinality of any subgroup divides the order of G. Now let us discuss direct products of groups. Let G1 and G2 be two groups. Definition, the direct product of G1 and G2 is the group defined as follows. So the elements of this group are pairs G1, G2, where G1 is an element of G1 and G2 is an element of G2. The product of these pairs is defined component-wise. So G1, G2 times G1 prime, G2 prime is by definition the pair where the first element is G1 times G1 prime. This is the product in the first group G1. And the second element is G2 times G2 primed. So this is a product in the second group G2. And the identity element in the direct product is just the pair E1, E2. So E1 is the identity in the first group, and E2 is the identity in the second group. Recall also classification of finite abelian groups. Every finite abelian group is isomorphic to a direct product of groups of the form Z with a lower index p to the power k, where p is a prime. Moreover, such decomposition is unique up to permutation of factors. So each finite abelian group is a direct product of cyclic groups whose order is a power of a prime. Finally, let us talk about group actions. So let G be a group and M a non-empty set. An action of G on M is defined as a homomorphism from G to the symmetric group on M, to the group of all bijective maps from M to M. An alternative description is as follows. An action of G on M is a map from G cross M to M, written in the following way. So the pair G, M goes to G of M, which has the following properties. E of M is equal to M for any M in M, so the identity of the group should act as the identity transformation of M. And G of H of M is equal to G times H applied to M for any M and G, H in G. This encodes the requirement that the product of G and H acts as the composition of the transformations defined by H and by G. So here are some elementary examples. Each group acts on any set via the identity transformation. So each element of the group acts as the identity transformation of this set. Next example, each group acts on itself by left multiplication. So G of M is equal to Gm for all G and M in G. Next example, each group acts on itself by right multiplication with the inverse. So G of M is equal to M times G inverse for all G and M in G. Here are some other examples of the group action. Each group acts on itself by conjugation. So G of M is equal to G times M times G inverse. So this is a combination of the previous two actions on the left and on the right. Example 2, S of x acts on x by definition. We already realized each element as a transformation on x. So the action is given by the identity homomorphism from Sx to Sx. Next example, d2 times n acts on R2 by definition. Again, an element of the dihedral group is by definition a transformation of R2. A less trivial example is that d2 times n acts on the set of vertices of the regular n-gon inscribed in the unit circle. This action is also by definition because d2 times n preserves the regular n-gon. And similarly, it also acts on the set of edges of this regular n-gon. Next example, if G is a group and H a subgroup of G, then H acts on G by left multiplication. So this is a restriction of the action of G on itself by left multiplication. Next example, if we have a normal subgroup in G, then the group G acts on its normal subgroup by conjugation. So this is possible due to the fact that H is normal. And the final example, if G is a group acting on M and H is a subgroup of G, then H acts on M by restriction. Let's now talk about orbits, stabilizers, and Burnside's lemma. Let G be a group acting on a set M. The G orbit of an element M in M is a set of all elements in M, which can be obtained when you apply an element G from G to M. The stabilizer of an element M in M is a set of all elements G in G which do not move, this element little m. And finally, the fixed point set for G in G is a set of all elements M in M which are fixed by the element G. So for example, we have the natural action of Sx on X. So for any element X in X, the orbit of this element under S of X is the whole of X. And the stabilizer of this element in Sx is naturally identified with a symmetric group on capital X minus the little x. So the little x should not be moved, and you can do whatever you wish with all other elements. And finally, let us recall the orbit counting theorem. Let a finite group G act on a finite set M. Then the number of G orbits on M is given by the formula 1 divided by the cardinality of G, sum over all G in G, and then we take the cardinality of the set of all fixed points of this element G in M. So this formula is also known as Burnside's lemma or Cauchy-Frobenius formula. At the end, a couple of problems and questions. Question number 1, let G be a group and G an element in G. Show that the binary sandwich operation x star y, defined as x times G times y, so such a binary operation defines on G the structure of a group, and determine the identity element with respect to this structure. Question 2, determine all subgroups of the group D2 times 4. Question 3, use coloring of the vertices of a regular triangle to show that D2 times 3 is isomorphic to the symmetric group S3. Question 4, describe all the orbits of the natural action of Sn on the set of all subsets of the set from 1 to n. And question 5, show that Gln k acts on k to the power n by left multiplication and describe the orbits of this action. Thank you very much and see you next time.